Continue from the previous video. So remember we talked about no matter what kind of distribution, what kind of shape, all the data, at least 88.88% will be in the range is average minus 3 standard deviation and average plus 3 standard deviation. But for the symmetric bell curve normal distribution, in the range of average plus minus 3 standard deviation, it's about almost everything because that's 99.73%. So here we can better see from the bell shape distribution here. In this picture, you can see that's what we call the central area. The central area, of course, the center is the average. Also, that's 0. So here, that's earlier we say minus 3 standard deviation from the average and plus 3 standard deviation. You can see they are almost everything because the tail, even they go longer forever, but that's, the area is very small. So that's here is more than 99%. So the other number is worthy to remember is the average plus minus 2 standard deviation. That's a yellow area. So this yellow area is 95%. Also, this 95% reminds you what? Remember a lot of, before when we talk about the confidence interval, we use a lot of time is 95%. So that's, you can see they are within the range, average plus minus 2 standard deviation. So this idealized version of the bell shape is we call the normal distribution. A lot of time in the real life, we do have similar shape. Of course, they may not so ideal, so smooth, but we can say they look like the bell curve and the normal distribution. So that's why in the next one, we will show you the example from the sample average. When we do the simulation many times, actually your histogram will look like the bell shape. So then from there, we can see they are really close to the normal distribution. Maybe not ideally, but close to. So then we see the example. We see the example to find the sample average. So back to our demonstration. So we go back to see our United flight information. So remember in the previous lectures, we used the United table. So here they contain more than almost 14,000 flight information in 2015 summer. So then we try to find the delayed data from this big data. So then you see the histogram from the delay. Yeah, this histogram, if you remember, yeah, we do have some data. A lot of data, they are between the -2 to the +2. They are kind of either no delay or they are arrive early or just 2 minutes delay. But since they have actually do have a big range, even to the 300, this one is minute, yeah, 300 minutes, like more than 5 hours delay. But they do have the data, even that's very small. But this distribution, what kind of shape it is? Yeah, actually that's skewed to the right a lot, right? They are not close to the bell shape at all. But one thing is we still can try to find from the distribution to guess what is the median, what is the average. So definitely we know the median will be very close to here. So then since they skew to the right, so then the average may be moved to the right. But we are not quite sure exactly, but we can find it out. Okay, so the first thing, that's our median from this distribution. Oh yeah, sorry, I didn't run that. Yeah, let's get the delay column. So we can see actually the 50 percentile is 2. So our median is about 2. So then of course we can get more information about the mean and the standard deviation. So you can see, like earlier we say, the mean will go toward to the right then that's the 16.65, more than 16.65. So then the standard deviation is very high, it's about 40. So here, actually, this table we have is kind of its population. So remember our purpose. Our purpose for the sample data is our sample data if we can draw by random and without replacement. So with replacement, so then we can have our data close to the population. So that's the sample. We care about the sample average because they estimate population average. So that's why here, let's see, even in our distribution, sometimes we don't know the population distribution, right? But anyway, here we have our population. Even the population itself, the distribution is not close to the bell shape. But one thing is, if we want to find the average, instead of to get all the data we calculate from the population about the average, how about we just do the sample data? Okay, so here, let's do the sample data. Let's have our one sample mean. So you can pass in the sample size. So then we just draw our sample from our population. So passing the sample size. So that's with replacement. Okay, so then you can have each time we return the average from one sample. So of course you can see we run this 100 size sample. Yeah, you have 14, you have 16, you have 24, you have 15. Yeah, so most of the time they are close to the population earlier we see, but they do have some big data as well. So before, like we say, right, one sample data is good, but one sample data cannot really reflect they have the differences in there. So that's why we want to have many estimation will be better. So since we have our population, then let's have our simulation. We do much more time to gather sample data. So we define 10,000 sample mean function. So the same thing here, you pass in the sample size you want. So let's do the sampling for 10,000 times. So then each time we have the new data, okay, the new mean. So we add to our array. So of course, after we done this function, we will have 10,000 sample data. And also this one is 10,000 sample mean. So then we pass in the sample size is 100. So that's why we got our sample mean is 100. So let's see how they look like. Okay. So of course, we are not want to see just array, right? So let's see that's in the histogram. So we have 10,000 data. Let's see the histogram. So then you will see the histogram. Wow, under the 10,000 simulation, not simulation, yeah, 10,000 sampling, our average for our delay time, they actually look like the bell shape, right? Not very exactly, but you can see from here, approximately you can draw the bell shape. And also we want to compare the population average is 16.65. So from here, if that's a bell shape, right? Okay, so then this definitely is our median and average. So you can see here is 15, then here is 20. So this one, right, is about 16 something. Okay, so that's how we can guess. Since you need to be more accurate on the scale to see that. So then if we really can check the scale, so then here is 16 something. Even from the distribution, we can guess that. And of course, that's called our NP average. So we pass in our array. So then we find the average is, yeah, it's 16.67. It's very close, right? Because the population actually is a 16.658. So our error actually within 0.02. So that's kind of good, right? Okay, so this one actually is, we show you, you get your sample average many times. They get the histogram close to the bell shape, regardless the original population distribution shape. So this one is we call central limit theorem. So the central limit theorem describes how the normal distribution is connected to the random sample average. So earlier, the random sample average is we show you, we take 100 size sample, but we do 10,000 times. After we got this 10,000 times mean, then we plug our empirical distribution. Then we find out that look like the normal distribution. We care about the sample average because they estimate population average. So this one also match we talked about before. Each sample is one estimation, but one estimation, they do have their variability and the differences from the population. But since if we can do as much sample as we can, then they will close to the population. And here that's we have. So here is what we have. That's we draw the sample size 100, then we do 10,000 times. The central limit theorem, they talk about regardless the distribution of the population, the probability distribution of the sample average is roughly normal. So this the normal, of course, we mean the normal distribution. But the most important thing is the sample need to be large and draw at random with replacement. So that's what we do earlier. So that's why we want to go back to see our demo. Our demo here, we're using the sample size is 100. Okay, so they kind of already very good to show the normal distribution. So how about we make our sample size is 400, and the same thing, we do 10,000 times again. So then we draw the histogram. Yeah, so that's take a while, right? Because earlier 100 already take a while, but now we do the sample size is 400 and we do the 10,000 times. Yeah, so you can see here, actually they are 100, this one is size 100, but this size 400 is even more bell shape. They just have kind of the range is a little narrow than the 100, because 100, you see, they still can go to 30. But here they kind of as far as 22.5. So then again, of course, that's compare. Even here we say, this is the bell shape, so we can guess that's the average. Also the average between 15 to 17.5. Also, of course, that's close to the 16.5. But of course, that's passing to our NP average. Oh yeah, so that's here. Even earlier, our size 100 is really close. But here, this average is still close to as well. So at least you see round to the first decimal place, they are close to the population average. But these two examples we show you is size 100 and 400. They are all very good already. But one thing is, we talk about the central limit theorem. Our size needs to be big enough. So that's why I want to show you, if we make the size a little smaller, maybe just 10, what will happen? Okay, so then we do everything become 10. And of course, we still do the 10,000 times. But then you plug on the result again. So you can see here, when we have the sample size from 100 down to 10, they are not look like the bell curve, right? They kind of more close to the population distribution. And also let's find their average. Yeah, the average actually changed to 10. Okay. So then you can see, yeah, the average is, yeah, it's a little more, but not too far away either. That's 16.79. But the most important thing is the distribution is not a bell curve. So that's earlier we say, when you do the central limit theorem, the sample size need to be large. We all draw at random with replacement, but the sample size is 10 compared to 100 and 400. The distribution of our sample average is not close to the normal distribution.